Assalamu alaikum and welcome to lecture number 25. In this lecture we are going to do some of the numerical problems on Fourier series, and we start a new topic, that is Fourier Transform. So you understand, in case of Fourier series we use the periodic signal, whether periodic signal are discrete or they are continuous. We use Fourier series, that is Fourier series for periodic signal, for continuous time signal, and periodic signal for discrete time signal. And you understand the coefficient of the Fourier series, whether they are discrete or they are for discrete time periodic signal, or they are from the continuous time periodic signal, they are discrete, right? That means the spectrum of the Fourier series is basically discrete spectrum, or we also call it line spectrum. Similarly, we will use the Fourier transform, which is used for the aperiodic signal. So because we know that aperiodic signal can be continuous in time, and they can also be discrete in time. So we use the Fourier series, Fourier transform for continuous time, Fourier transform for the continuous time signal, and we have also its discrete version. So we also have discrete Fourier transform for the discrete aperiodic signal. And you will learn that in Fourier transform, basically spectrum is continuous, so that means we have continuous values of the frequency, right? So whether it's a discrete times aperiodic signal or the continuous time signal, in both cases we have continuous spectrum. So let's see. So here we are given two impulses, in fact impulse trains, right? One in discrete time and one with in continuous time, and we have to find the Fourier series coefficient for these. So okay, I'll try one here, and one is your homework. So maybe I just go for the continuous case. Okay, so in continuous case, you know how to find the Fourier series coefficient. So you understand that AK equals to integration 1 over t, right, over 1 in period, that is t, and we have x of t and e power minus j k omega naught t and dt. Okay, so similarly for discrete time, you understand it will be 1 by n summation over period, and that is x of n e power minus j k capital omega naught n. So it will be by putting values. So you can see this is a periodic train. Okay, we are doing this one, right? Periodic train, and if you plot it, you will understand basically this has period n. So it will be 1 by n, and then we integrate it over n. So it will be, for example, we take integration from minus okay, so we take one period from minus n by 2 up to n by 2. Okay, so this is the impulse of t and e power minus j k omega naught t and dt. So you understand impulse has value 0. Okay, from right, if I plot the signal, it will be something like this. For example, at 0 it will have value 1, then it is 0, and then here this is, for example, n, right here this is minus n and so on. So this is, for example, 2n, right? This is t, and again, for example, this is minus 2n, and this is continued. Okay, so we take the interval that is from, for example, this is minus n by 2, and this is minus n by 2, and this is n by 2. Okay, so you understand the impulse will have value equal to 0 for all values except where its argument is 0. So the argument of it is t. When t is 0, its value will be 1. So that means if I put 0 here, that means from minus n by 2 up to n by 2 for all values it will be 0 except at the point where its argument is 0. So at that point it has non-zero value, so it will be 1. So that means at t0 it will have value equal to 1. So that means when t is 0, I put 0 here, it will become e power 0. E power 0 is 1. So that means I get this is equal to 1 by n. Okay, so this is the coefficient, Fourier series coefficient for the continuous time case of the periodic impulse train with period equal to n. Okay, so that means it's, if I find its magnitude, so it's how to say, it's a constant, right? So its phase is 0 and it is independent of frequency. So at all frequencies it exists, right? So if you take k equals to 0, k equals to 1, whatever, but it's a constant one. I hope you can do the second part, yes, the first part by yourself, which is the discrete time case. So here we take another example for the discrete time case, and in this case we are given the magnitude response and the phase response, and we are asked to find the time domain signal for this. So the equation that relates the time domain signal with the frequency domain is x of n equals to summation. Again, you understand that we are summing it over one period, that is k equals to 0 up to n minus 1, or we can take any one period. Okay, and ak are the magnitudes which are plotted here, and omega naught, k omega naught is the frequency. Okay, so let's reconstruct the signal from this given information, which is phase response and magnitude response. So if we look at the magnitude response signal, we can easily tell what is the period of this signal. Okay, so starting with 1 at 0, right, the signal has value of 1. At index 0 it has value of 1, and again at index 6 it has value of 1. So that means its period is 0 to 5. So 0 to 5 means it has a period of how much? Is it 6? No, it's not, because it's not repeating at this. Okay, so that means you see two dots here, and that means two zeros here, and again we have two zeros at which point? Or maybe we start from here. So we have 0 here, and so if I just write here, for example, this is minus 4, and this is plus 4. So if you look at carefully, you can observe that from minus 4 up to plus 4, right? Afterwards it is repeating. Hope you understand. So at minus 3 it has the same value as at plus 6. Okay, similarly at minus 2 it has same value as at 7, or at minus 1 it has same value as at 8. Similarly at 1, right, it has same value as at 9, not at 1, in fact at 0, right, this is 0, so at 0 it has same value as at 9. Similarly at 1 it has same value as at 10, so 10 minus 1 means 9, or 9 minus 0 means 9, or 8 minus 2 mean minus 1 means 9, right? So that means it has period n equals to 9. Okay, so let's take the corresponding magnitudes and the phases. So let's take the interval of k from minus 4 up to 4. So minus 4 up to 4 makes 9, right? You can take any interval. You can also take from 0 up to 8, right? Because at 9 it will be it is repeating, right? So it has same value at 9 as at 0. So that means from 0 to 8 can be one period, or from 1 up to 9 can be one period, or from 2 up to 10, right? And you understand you can take any period. So let's take the period from minus 4 up to 4. So let me expand this equation from minus 4 up to 4. Okay, so I have expanded. So now you can see that this is right your magnitude response, and this is the phase response. So if I expand this equation, and we have found that the period is 9, so we take the summation from minus 4. You understand this summation can be taken on any period, so we are taking it from minus 4 up to 4. So if I open this equation, that ak of minus 4, so minus 4 is 0, that's why I put 0, because anything multiplied by 0 will result into 0. Then at minus 3 we have amplitude equal to 1, so if I open this, so 1 and e power, for k I have written minus 3, right? At this minus 3 we have the phase equals to, you see this is pi by 3 and this is pi, so that means this is basically 2 pi by 3. So the phase will be 2 pi by 3, then plus 2, this is the here, so the corresponding phase is pi by 3, so 2 into minus j2 omega naught n into e power j pi by 3 plus 0, because at minus 1 it has value equal to 0, so anything multiplied by 0 will result into 0, plus at 0 we have 1, so 1 multiplied by e power k is 0, so e power j 0, right? And what is the phase here? So the phase here at 0 is basically pi. So you understand e power j pi, this is the phase. So this basically corresponds to the value of minus 1, because e power j pi, if we write it into the real and imaginary part, so it will be cos of j pi and plus j, not j pi, cos of pi plus j sine of pi. So sine of pi is 0 and cos of pi is minus 1, so it will result into minus 1, right? Similar arguments applies to these. Now let's take the corresponding values, right? So to take the corresponding values, this is e power minus j 3 omega naught, right? and its corresponding value is this one, e power 3 omega naught, right? So this is your first pair. So similarly we can write for this second one, this is e power j 2 minus 2 omega naught, and this is e power j 2 omega naught. So this is another pair. So others are 0, so just we write it like, so it will be something like e power, right, e power minus j. So because this is positive, so let me write the positive term first. So this is 2. Okay, or let's start with this one. So this is e power minus j 3 omega naught, and this is plus 3 omega naught. So let me write first this, because this is positive, so this is okay. So we can just delete this one and we can write e power, right? So if I take j common, I am left with 3 omega naught and minus j 2 pi by 3, right? Okay, so I'm writing the corresponding terms, the corresponding harmonics. So this is 3 omega naught e power j 3 omega naught and minus 2 pi by 3, which is this term. Okay, and its corresponding is this one. So this is, again, I have written here and I've just taken minus common here, so it will become 3 omega naught and minus 2 by 3 pi. Similarly, 1 into e power j 0 will result into 1, and e power j pi will result into minus 1. So 1 multiplied by 1 multiplied by minus 1, so it will result into minus 1. Similarly, I have taken 2 common from here and doing the same logic, based on the same logic which I did here. So I have written this one. Now this is similar to the, or in fact same to the similar to the cos. So if I divide it and multiply it by 2, so you can see this is basically cos. And again, if I divide and multiply it by 2, so I will get the cos term again here, right? So that means this is basically cos, so it will be 2, right? 2 into cos of, what is the angle? That is 3 omega naught and minus 2 pi by 3, right? And minus 1, which is this one, and plus 2 2s are 4, so it will be 4 cos into 2 omega naught and minus pi by 3. Okay, so this is how you can construct discrete transform the using Fourier inverse transform to obtain the continuous time counterpart, or the continuous sorry, not continuous, the time domain signal, right? So here we are given the frequency domain signal. This is the magnitude response for that, and this is the phase response for that. And using both of these, because you understand the Fourier coefficients, whether they are in discrete or they are continuous, they are basically complex. So when something is complex, it has magnitude and phase, or you can also write it in rectangular form. So you can say that something is complex, it has magnitude, it has real and imaginary part. So I hope you understand both the notation, because this topic we have discussed so many times, right? So first, by looking at this, you can find what is the period of this signal. So by looking at it, the period is found to be 9. So when the period is 9, then you can take from 0 up to 8, or from 1 up to 10. So whatever you want to take for summation. So we are taking here the summation from -4 up to 4, and by putting the values in this equation, right, you understand. So you put here, and you also, because you are given the phase response which is not 0, so you have to mention the phase here also, right. So starting with this one, the first one at -4, this is 0, so we straight away write 0. Then at -3 we have amplitude equals to 1, so that's why I have written equal to 1. And in this expression, right, we are writing the values here. So for k equals to -3, a of -3 basically equals to 1, so I have written 1. And e power minus j, right, so we write -3 omega naught n, so minus is here, so that's why it's minus j3 omega naught n. Then by looking at the phase response, we can see for -3 the phase is this one. So this is, you see, this is the pi by 3, and this is pi, so that's definitely 2 pi by 3. Okay, so similarly this one is 2 pi by 3. So and also it is how you write the phase. So you have to mention the phase with these, right. Once you have done this, then you take the corresponding harmonics, that is harmonics that are having the, you understand harmonics, right. So the first harmonic, the second harmonic, right. What are harmonics? Harmonics are the integer multiple of fundamental frequencies. So the corresponding harmonics will be, this is 3 omega naught -3 omega naught, so its corresponding will be +3 omega naught. Similarly for -2 and +2 and so on. So using this you can find this one, and once you know, this is the expression for the discrete time signal, right. Also one more thing we can do, which we did not, is the replacing the value of omega naught. You understand the value of omega naught is because it is related to the period, so omega naught equals to 2 pi, because period is given, so 2 pi by n, right. So in this case we are given n equals to 9, so this will be 2 pi by 9. So you can replace here, I just write with the different color of pen the values for frequency. So this is 2 pi by 9, so 3 multiplied by 2 is basically, let me write different color, so it will be 6, you understand, 6 pi by what, 9, right, 6 pi by 9, and again it will become 2 2s are 4, so 4 pi by 9. And so I hope this gives you the idea how we can reconstruct or transform how we get the time domain signal from the frequency domain signal. So in case of square wave, you understand that we have infinite Fourier series coefficients, right? So to gain understanding of the square wave example, and more generally of the question of validity of Fourier series representation, let's examine the problem of approximating a given periodic signal by linear combination of finite number of harmonically related complex exponential. You understand we have infinite coefficients, right, to reconstruct the original signal that we have the coefficients k running from -infinity up to infinity. So what will happen if we use just the finite number of coefficients? Let's we have from -n up to n, right? So of course this truncated Fourier series is not exactly equal to the actual signal x of t. So we denote it by we denote the error signal ENT by right? The error signal by E and T, and we say x of t minus x of nt, which is its approximation or truncated Fourier series. So because truncated series is k running from minus infinity minus n up to n, whereas in the original case it is from minus infinity up to infinity. So we get the error signal, and the to know how good any particular approximation is, the criteria we use is the uh, error, right? The energy in the error signal over one period, which is represented by this one. Thus, we obtain the best approximation, right, by minimizing the error. So we are just using, remember that we are just using finite number of harmonically related complex exponentials. So we call it truncating the Fourier series to the desired number of terms, for example, n here. So you understand, as n increases, that means we are adding more and more terms. So definitely the error will increase, and subsequently the error energy will be minimized. And if n approaches infinity, in that case the truncated Fourier series signal x of nt and the original signal, they will be same. So that means the energy will tend to 0. Right? So next topic is about the Gibbs phenomena. So you understand, for a periodic signal that has no discontinuities, the Fourier series representation converges, and it is equal to the original signal at every value of the t. However, for a periodic signal with finite number of discontinuities in each period, the Fourier series representation equals the signal everywhere except at the discontinuity, right? And at that point, it converges to the average value, right, on both sides of the discontinuity. So this is an interesting phenomena which is observed by the American physicist named Michelson. As can be seen from the figure, this is basically again about the square wave signal, right? So in the case of square wave, you understand we have discontinuity. This is a discontinuity, and here is discontinuity. So Michelson, actually an American physicist, constructed a harmonic analyzer, right? And what is a harmonic analyzer? It's a device that for any periodic signal would compute the truncated Fourier series approximation. He tested his device on many signals and got the desired or the expected results. But when he tried the square wave, he obtained an important, to him, very surprising result. He thought maybe there is a defect in his device. Michelson observed that in the vicinity of the he observed that the behavior of the partial sum in the vicinity of the discontinuity exhibits ripples as shown here. Like you see ripples here, here, again this one, right? This one, and so on. So in all the figures around the discontinuity, he observed there are ripples. So he started increasing the number of coefficients, but he observed that as the number of coefficients are increased, the amount of the peak amplitude of the ripple does not seem to decrease. He wrote this problem to the famous mathematician Gibbs, Josiah Gibbs, right, who investigated it and showed that these are in fact the case, specifically For the discontinuity of unity height, the partial sum exhibits maximum value of the overshoot of 9% of the height of discontinuity, no matter how large n becomes. So thus, as n increases, the ripples in the partial sum becomes compressed towards the discontinuity. But for any finite value of n, the peak amplitude of the ripples remains constant. This behavior has come to be known as Gibbs phenomena. So this is about the Gibbs phenomena, right? So if you have any question, you can ask in the live session. Hope this clears. From these slides and onward, we are going to start a new topic, that is Fourier transform. Fourier transform is used to convert the time domain signal into the frequency domain signal, similar to what is Fourier series, but the only difference is that we use the Fourier series for periodic table, right? Periodic signals. Fourier series is used to convert the time domain signal to frequency domain, but for the periodic signal, whereas the Fourier transform is used for the conversion of the same thing, but now this is used for the case when the signals are aperiodic. So similar to the Fourier series, we have expression, we have the analysis and synthesis equation. This is the analysis equation, which is used to convert the time domain signal into frequency domain, and this is the synthesis equation, similar to what we had in Fourier series, right? So if you compare the Fourier series in Fourier transform, the synthesis equation has the scaling of 1 by 2, whereas if you recall, in case of Fourier series, the scaling was in the analysis equation where it was 1 by t for the continuous time case. Similarly, the Fourier transform used for discrete time signals is called the discrete Fourier transform, and it has the analysis equation as this one, which we also can say that this is basically conversion from the time domain into the frequency domain, so that you can see in this formula the input signal is the time domain signal, whereas in the output we get the frequency domain signal, right? And this is again, so because you understand the discrete time signal, the maximum frequency range is from 0 to 2 pi. That is, signal's frequency increases from when we move from 0 at pi, it becomes maximum, and when we move from the pi away towards 2 pi, the signal starts decreasing, the frequency of the signal start decreasing, and it has the same frequency as at 0. So that means the maximum frequency range for the discrete time signal is 2 pi. So that's why we are integrating it over 2 pi. So this is the synthesis equation for the discrete time case. You understand that in discrete time case, the signal input is the frequency domain signal, and using this equation we get the output, which is the time domain signal. So if we compare the frequency domain, the continuous time Fourier series with the continuous time Fourier transform, in case of continuous time Fourier series, it is used to obtain the frequency representation of a periodic signal, right? And the basis signals here is or the basis function is e power minus j omega naught t, right? And the complex exponentials or the amplitudes we get, we represent them by ak. But in case of continuous time Fourier transform, we use it to obtain the frequency representation of an aperiodic signal, the basis function is e power j omega t, okay, defined at frequency omega, which is a continuous, right? So you understand, if you compare the two, the coefficients here, they were discrete, right? So we had the values of the coefficients at a0, a1, a2, a3, a4, and so on, or similarly minus a1, minus a2, minus. So these, we can say the magnitude spectrum of the discrete of the continuous time periodic signals was discrete, right? So in case of periodic signal, we have a discrete spectrum, whereas in case of the aperiodic signal, where we use the Fourier transform, so we have a continuous spectrum, right? The coefficients of the Fourier series was represented by ak, whereas here the coefficients will be represented by x of j omega. In fact, x of j omega is a continuous. So let's have some numerical examples to elaborate it more. So consider a signal which is x of t e power minus at u of t, and a is greater than 0. So when a is greater than 0, it signifies that basically this is exponentially decaying, right? So if the a is less than 0, that means a will have negative value. So if you multiply this negative with this one, so the resulting signal will become exponentially growing signal. Okay, the other important thing is that we are multiplying u of t here. So that means if you multiply u of t here, this signal basically exists from 0 up to infinity, right? And for the negative values of the t, it will be 0. Why? Because u of t is multiplied here. So you understand, u of t is basically mathematical. We can call it a mathematical switch, which can turn on and turn off. So it basically turns on when its argument is equal to or greater than 0, and it stays off when its argument is less than 0, right? So to find the Fourier transform of this signal, let's apply the formula. So we know that x of j omega, which is the Fourier, let me change the color. So let's take this color. Okay, so x of j omega basically equals to, if you recall, because we have shown you the formula on the previous slide, so it is from by writing the equation, so the equation is x of j omega equals to minus infinity to infinity x of t times the e power minus j omega t dt. But because x of t is here e power minus at u of t, so that means u of t signifies it will be integrated from 0 up to infinity. So I write here 0 up to infinity e power minus at e power minus j omega t dt. So if I take, their multiplied bases are same, so I can write it on the same basis. So here I am also taking minus t as common, so it will be a plus j omega, right? So this whole will simplify into this one. The integration of this is same, but just the scaling factor, that is, you scale it divided by minus a plus j omega. So by putting the limit from 0 up to infinity, the upper limit is infinity. So if I put infinity here, we have anything multiplied by infinity will result into infinity, and because we have minus here, so e power minus infinity, right? And minus e power, again I put replace t with 0, so e power 0, e power minus infinity minus e power 0, so e power minus infinity is basically 0, and e power 0 is basically 1, so I will have 0 minus 1 means minus 1, minus this minus and this minus cancel, so I get this value. So you understand, this is the Fourier transform x of j omega, and you should know that x of j omega, similar to the Fourier series coefficient, is the is complex. So you understand, if something is complex, then we have its magnitude and we have its phase. Now how to plot the magnitude response and the phase response. So I hope you understand. You take different values of the frequency, right? We have done similar example maybe once or twice, so using that you can do it. Again, we can take the phase response. So phase response, you understand, is basically the I think we represent it like this. So this is x of j omega. What is the phase of this? So the phase of this can easily be found by the expression that the phase is basically equals to tan inverse imaginary over real, right? So because this is in denominator form, that is, we have something like this, a plus j omega, right, which I have mentioned there too. So that means the net phase will be equal to the phase of the numerator minus phase of the denominator. But in case of numerator, we have only the real component, and the phase is basically equals to tan inverse imaginary over real. So that means imaginary is 0. When imaginary is 0, that means this is basically a zero phase, right? So that means 0 minus tan inverse of, what is the imaginary part here? That's omega, and the real is a. So 0 minus tan inverse of omega by a. So that means you have 0 minus anything that is negative. Now again, you put different values for this one. You understand we have negative values for frequency. So you take omega equals to 0, okay, and find the phase. Then omega equals to, for example, you take as 1 by a, right? And you find, and again you take omega equals to, because I can write here minus this, okay. First you find for the positive omega, then you take omega equals to infinity, right? So using these values, again omega equals to 0 is same, but you take omega equals to, for example, minus 1 by a. And for the third case, you can say, okay, omega equals to minus infinity. Thus you take negative frequencies like here and positive frequencies here, and you find the magnitude response, and you also find the phase response. And remember that the independent variable will be omega, so you'll get graph something like this. This is for the magnitude response, right? So you understand this behaves like a low pass filter, because at 0 frequency it has maximum magnitude. When you move from the frequency 0 in either direction, you observe that frequency, the response is basically decreasing. So that means it is behaving like a low pass filter, or in fact it is a low pass filter, right? So you can compare this equation which we have already done for the finding. If you recall, we were given impulse response for the filter, and we have to find the frequency response. If you recall, I think it was lecture number 21 or maybe 22. So you can go there, and or if you know, so it's similar to what we had. Okay. So I hope you can plot these. I want you to do it by yourself, because this is just for your reference, that you get the right answer or you get the wrong answer. And if you get the wrong answer, you can discuss with me, right? Or even if you get right answer and you want to discuss, so you are welcome, and in the live session we can discuss this one. So with this we end the lecture, and see you in the live session. Okay, so you must go through all these slides, and we can discuss it in more details, many things, in the live session. Okay, Allah Hafiz.